Well, greetings, mathletes, and welcome back. And we're going to be finishing up our lecture on radicals today. So we have two orders of business to handle today. Um, First, we need to talk about rationalizing the denominator, right? Um, and then the second thing we need to talk about is rational exponents. All right, so those are the first things we're gonna hit today. Oh, we're having a really rational discussion. Yes, um, I'm not sure I want to hear you criticizing my jokes after that, but okay. Um, so let's take a look. Let's go ahead and start with rationalizing the denominator. Now, when we talk about rationalizing in math, it really does mean something different than it does in English. Usually, when you're talking about it in English, rationalizing means that you're trying to make things make sense. But in math, it actually has to do with looking at a ratio. So if you look at the word rational, there's the word ratio in there. And so rational numbers are numbers that can be expressed as a ratio of whole numbers. So when we're talking about rationalizing the denominator in the context of roots, what we're talking about is taking something that looks like this and getting rid of the radical in the denominator because radicals are not a rational number. So that's the idea. Now, there's a very practical reason for it, although with the advent of calculators, it's not quite as important as it used to be. Um, something like the square root of 3 has an infinite decimal. And if you're actually doing this division longhand, it's very difficult to have an infinite decimal divisor. So what we do instead is change the divisor, change the denominator so that it's a whole number because that's a lot easier to divide into something else. So if we look at this thing, we have to be able to alter it so it doesn't change its value, but it has a rational number at the bottom. So if we think about things we're allowed to do with fractions that don't change the value of the fraction, probably the most common thing to do that doesn't change the value is to multiply the numerator and denominator by the same number. That's always legal as long as you're multiplying top and bottom by the same number, as long as you get both of them. Everything you multiply will be legal. So we have to ask ourselves, is there something I can multiply the square root of 3 by to get something that doesn't have a root? What if you square it? Squaring it's not a bad idea because squaring it does cancel out the root. But here's the problem. If you take something and square it, you're multiplying it by itself. And that's going to change the value. What I'm multiplying on top doesn't match what I'm multiplying on bottom. But you notice on the bottom, the square root of 3 times the square root of 3 gives me 3. So that might be my ticket. If I multiply the top and the bottom by the square root of 3, instead of trying to square the whole thing, that will square the bottom. It won't square the top, but it will square the bottom. And so what you end up doing with these, you want to make sure your root is simplified first, and we are in this case, we're simplified. And if I multiply it by the square root of 3, that will give me a 3 in the denominator. Let me do this. Let me get this off of here so it doesn't look like it's part of the computation. There we go. That'll give me a 3 in the denominator, but the rules of fractions say I have to multiply the numerator by 3 as well. And so 2 times root 3 is 2 root 3. And so now we have rationalized the denominator on this because the denominator is now a rational number, right? So when you have a single root in the bottom, when you have a single term in the bottom and that term has a root, you just basically what you end up doing is multiplying numerator and denominator by that root. So if I have something a little more complicated, I'm going to make it, well, let's just do this. Let's say I have something like this. And let's say it is the square root of 18. Okay, so my goal here, if I'm going to rationalize my denominator, is to get rid of that square root of 18. Now, the square root of 18 can reduce though. So we do need to reduce this first. So if we do that, right, we got our prime factorization. The square root of 18 is, let's see, I have a pair of 3's and I have that 2 left over, so I have 3 root 2. Okay, now 3 is already a rational number, so if I'm going to be clearing out the root here, all I need to multiply is root 2. So let's go ahead and take a look at that. So if I multiply by root 2, my denominator, well, root 2 times root 2 is just 2. So now this is 3 times 2. And then up here in the numerator, well, let's see, what do I get here? 2 plus root 10. Okay, so you're saying it's 2 plus root 10. Here's a problem. That's not multiplying the entire denominator, right? Or excuse me, the entire numerator. If I look at this, anytime you have a numerator, even if the parentheses aren't there, there are parentheses around that. And so this actually has to be distributed here. So this guy is actually wrong. That is not what needs to be there. What we actually end up with, we do end up with the root 10 from this distribution, but over here we end up with, oops, there we go. Why is this not writing for me? Oh, because I don't have it on the thing that writes. Okay, let's try it again. 2 root 2. And so I end up with 2 root 2 plus root 10. And this is, I have 2 times 3 here, but our final answer would be 2 root 2 plus root 10 over 6. And so the trick is here that you actually have to multiply the entire numerator. You can't just multiply one term. If you miss one of those terms, you will get the wrong answer. Mr. Brian, can't we reduce that? Why do you say that? Oh, they got 2's in them. That's right, they do have 2's in them. 2 and 6 could reduce, but here's the problem. This is all one numerator. If I'm going to cancel a 2 out, I have to be able to cancel a 2 out of every single term here. Right? And these numbers, the 10 and the 2, can't be canceled out unless you have something inside of a root, because they're trapped inside this root here. So the 6 can't touch those guys. And there's not a 2 in the second term here, so you can't do anything with that. There's nothing you can actually reduce here. You could reduce it if you did this, right? If you broke it up like this, you could reduce here and change that to a 3, right? That would be legal. But you can't do it to the whole thing unless you can cancel it out of both terms, because you can see here, this one still keeps it 6 when you do that. So you got to be real careful with that. But this would be your final answer. And that is perfectly reasonable. Okay, so that's actually our first case. When you have a single term, you have a monomial term in the denominator. If there's a radical in there, you just need to multiply by the radical, whatever that radical happens to be. Okay, so let's go ahead and clear some of this off here, and we'll take a look. Okay, for the second case is when you have a binomial in the denominator, and that means there's 2 terms in the denominator. And as long as one of them is a radical, this is what we do. And it could be both of them that's a radical as well, just so we're aware. But in any case, the thing we're going to have to remember for this is this little property from algebra. if I'm multiplying something that looks like this is called the difference of squares. And it's called the difference of squares not because I'm looking at squares here, but because when I multiply this out, I have one square and I'm subtracting another square from it. It really is a difference of squares. And this is the property that we're going to be using here. I'm going to go ahead and erase the name here so we have a little room to deal with this. So if we're, I don't know, walking down the street and someone jumps out from behind a dumpster, this seems to happen a lot in my neighborhood. I don't know why. But if I have something like this, right? Now I know what the gut instinct is, right? What does your intuition usually tell you? Multiply by root 5. That's right, multiply by root 5. But let's look and see what happens when I do multiply by root 5. So if I do that, what you end up wanting to do is just multiply these two. But if we take a look at this, I actually have to distribute this. So if I multiply it out the way I have it right now, I get 2 root 5 on the top. And on the bottom, I multiply this, I end up with 3 root 5 plus 5. And you notice I didn't get the root out of the denominator, right? It's still there. And so we have to do something else here. Let me go ahead and erase all this. See if I can get that off without ruining my problem. There we go. It's so much easier on the whiteboard when I can just use my finger to clean those things off. Here's what we end up doing instead. Because of this property up here, right? And I'm going to work this one out two ways. I'm going to work it out the long way, and then I'm going to work it out using a shortcut. But if I look at what's here, oops, is it that one? Nope, that's not it. Let's try this again. There we go. Okay, if I look at this property here, what I end up with is the square of each one at the end. And so what we do when we have two terms in the bottom is we multiply by the conjugate. So if this is one term, the term with the opposite operation is the conjugate. So if I want the conjugate of 3 plus root 5, the conjugate will be 3 minus root 5. And that means I have to multiply the top by that as well, right? Because top and bottom have to be multiplied by the same thing. Now, this denominator, I'm going to work it out using the box over here so we can see what we got. So that means I have 3 plus root 5 across the top and 3 minus root 5 across the side. Let's see, 3 times 3 is 9. 3 times root 5 is 3 root 5. 3 times negative root 5 is negative 3 root 5. And root 5 times negative root 5 is going to give me negative 5. Okay, so if we look at this, you'll notice right here in this part that this, oops, there we go, this and this cancel each other out. They're opposite signed. The terms are the same except for their sign. And so all I have left is to add these guys together. 9 plus negative 5 is 4. And so that denominator turns into a 4. Okay, so that's the long way to do it. You can always, if you're unsure about how something's going to come out, you can always turn over to the box and just multiply it out, right? Have enough patience to be able to do that, because you do it a couple of times and then you start figuring out the shortcut is what happens. So here's the shortcut. Since this is a plus b times a minus b, and I know that the answer is going to be the difference of squares, right? And that's from this property up here. What I can do is say, oh, well, this is a plus b, and this is a minus b. So that means what I should get is a squared minus b squared. Well, a is 9, so this is, or excuse me, a is 3, so this is 3 squared, and b is root 5. So I have root 5 squared. So if you just square both terms and subtract them, you'll get your answer. So this is 9 minus, and again, a square cancels a square root. So this is 9 minus 5, which is 4. You can typically do this in your head, right? And I have no problem with people doing this in your head. You don't necessarily have to write everything I did. You can just look at this and go, oh, let's see here. I'll switch colors. 3 squared is 9. Root 5 squared is 5. And then I'll distribute the top. 2 times 3 is 6. 2 times negative root 5 is minus 2 root 5. And so what we end up with is 6 minus 2 root 5 over 4. Okay, now that is a correct answer, but there is a problem with it. What's the problem here? Can you reduce it? Yes, you can reduce it. Yeah, and this is one of those cases, I was talking about this before. If you have a common factor to every term, you can cancel that common factor out. So in this case, all of the coefficients here are even. So that means I can divide them all by 2. So I can make this into a 2, that turns into a 1, and this turns into a 3. And so if I rewrite my answer, I end up with 3 minus root 5 over 2. Right? And so these tend to get a little bit more complicated because you have that binomial multiplication. And I did fill in a lot of extra stuff. So it does look like more work than it actually is because I was explaining everything as we go. But let's go ahead and see if we can work out a problem on our own. So let me go ahead and clear this off and we'll look at another one here. Not that one, that one. So let's go ahead and clear that off, clear that off. There we go. Now we're ready to rock and roll. So this is one of those problems. I want you to pause it, see if you can work it out. And then once you work it out, you can watch my solution. So go ahead and pause it here. I take that back. Don't pause it here. I haven't written the problem down yet. I'm getting ahead of myself. You're losing your mind, Mr. Brian. Yeah, I am. Okay, so let's get started here. So let's say I have root 2 over root 2 minus root 5. Okay, see what you can do with that one. It's the same process as we did last time. So this is actually the place where you pause it. Okay, so presumably you've worked on this one. Let's go ahead and see what we can get done here. Yeah. All right, so I look at this thing, and here's what I'm thinking immediately. I have a binomial term, and at least one of those terms is a root, so I need to use the conjugate. So that means I'm going to multiply the denominator by root 2 plus root 5, and the numerator by the exact same thing. Okay, now I'm going to use that shortcut. All I need to do is square each term in the denominator here and then distribute the numerator. So let's see what we got here. So that means my denominator is going to be root 2 squared, which is 2, minus root 5 squared, which is 5. So that went really fast. I didn't have to put in all those other details. It just knowing the formula and going from there. And then in the numerator, I just need to distribute this. So root 2 times root 2 is 2. Root 2 times root 5 is root 10. And so now if I simplify my denominator, this is 2 plus root 10 over negative 3. Now, it is not typical to write the negative in the bottom. That is, what's the word I'm looking for? It's unusual. There are times when it makes sense to do so, but most of the time you want another form. So when you write these, I'm just going to rewrite this problem here and then show you the different forms that are all correct. Typically, the way you write it, either the negative is in the numerator or the negative is out front. So you could do this. right? And so the negative can choose which direction to go. It'll either go to the top or to the bottom. The other thing you can do is take this negative and distribute it across the top. So this is also a correct answer, right? So both of these, or all three of these, are actually correct answers. And you notice the difference in the placement of the negative, right? You can go bottom, out front, or distribute it through the top, right? Oh, I should say here, right? So there are different forms of this. And we look at it, I don't see anywhere that this can distribute. There's no common factors other than one. And so this right here ends up being my final answer. Well, either of these. I think this middle one's probably the easiest to write, so I'm going to write that. So it's the negative of 2 plus root 10 over 3. And the reason I chose the middle one is entirely aesthetic. I just think it looks better. Typically, the two forms that you'll see in the answer are these two. Those are the ones that you generally see. You usually don't see a negative in the denominator. All right, good. So let's go ahead and clear this off. And we'll start talking about rational exponents. Okay, so rational exponents. So if you're dealing with a rational exponent, it actually looks something like this. Oh, let's try it where we're actually drawing things. Okay, you'll see things like this, where the exponent is a fraction. What in the name of Isaac Newton does that mean? Well, that's a really good question. That's what we're going to talk about here. Okay, so I'm not going to go through the entire process of doing this because of deducing this, just because it's going to take a lot of time. I'm going to hit the high points here. But this is based on this idea. Okay, if you have some number raised to a fraction, so we'll put n over m. Okay, so if you have a fraction that looks like this in the exponent spot, you can actually convert this to a root. The denominator is the index of the root. Oops, that is not how I wanted to write that. Ran out of room to finish the m. Let's try this one more time. Right, so the denominator is the index of the root, and the numerator, well, there's two places you can put. Technically, what you're talking about is putting it out here. Actually, let me write that a little neater. Okay, so let's try this one more time. It's the nth root of x raised to the n power. That's technically what it means. And that is the most complete definition. However, there are a lot of times when it is much easier to write it this way. And this is typically correct as well. The only time that it is not correct, this piece right here is not correct. This only works if x is greater than or equal to 0, right? Because if x is the negative number and n happens to be an even number, it'll hide the negative when you do it first. So as long as you know your x is positive, you can actually write it that way. Which honestly, in a lot of these textbooks, there'll be some little thing that says make sure x is positive so that you can use that. Okay, so now that we have this definition, let's go back and look at this 8 to the 2/3 thing. Because, when we look at an exponent, we think of it as how many times something is multiplied by itself. And how do you multiply something by itself 2/3 of a time? So this is how it ends up playing out. If we just use this definition, this is the cube root of 8 squared. That's actually what we're looking at. Well, the cube root of 8 is what times itself 3 times will give me 8. And so that answer is 2, right? The cube root of 8 is 2, so that now this is 2 squared, and so my answer is 4. So 8 to the 2/3 power is 4. right? I think that's actually kind of cool. Excuse me. And you can look at it another way too. Um, this is, I don't know, this is probably a little extra something that might save you some computation in the long run, especially when it comes out to a whole number. 8 is 2 to the third, right? If I raise 2 to the third to the 2/3, what I'm going to be doing here is multiplying those two exponents. The rules of exponents still apply. 3 times 2/3, well, if I put that 3 over 1, I can cancel it. That gives me 2. So that's kind of interesting. So that means now this is equal to 2. Well, 3 times 2/3 is now 2. 2 squared, which is 4. So that's a second way to work this out. If you rewrite the number in terms of its prime factorization, sometimes you can simplify these things this way. Um, so this is basically how it works, right? So let's see here. Let's go ahead and clear this off. I'll leave that there. And we'll do that. There we go. Okay. Yeah, let's see what we can do with this. Let's say I have, let's say I take 9 to the 3/2 power, right? So let's see if you can compute this. Go ahead and pause this. Okay, I'm assuming you've paused and looked at this now. So, if one of the skill I really want you to be able to have is to rewrite these things in terms of roots, right? Um, but computing them is also important. So, if we use the root property, this is now the square root of 9 raised to the third power. Square root of 9 is 3, so this is 3 to the third power, and 3 cubed is 27. Right? So that's actually kind of a nice way to look at it. Now, the next thing I want to look at, let me switch colors here, is, if you're just writing things from one form to the other, and that's quite often that's the only thing we really need to do because it's an in-between step in solving some kind of problem. If I have something like 3x to the 4/5 power, right? You're not going to be simplifying that down to a single number, right? It's just not going to happen. 3 is a prime number. It doesn't have any roots that are nice. So what we end up doing is just using the definition to rewrite this thing. So I know in my root I'm going to have 3x. The denominator tells me that I'm going to have a what do you call it? An index of 5, and the numerator tells me that I have an exponent of 4. Now that's all fine and dandy, but when you have a number in there like that, we know the number's positive, right? And in the problems in your book, you're probably going to be assuming x is positive as well. And so as long as that's the case, or excuse me, not positive, non-negative, because it can be 0. What I can do is look at it this way. And typically you do this when there's variables involved, right? You look at it as the exponent being on the inside. Then using rules of exponents, we can distribute this exponent across multiplication. So 3 to the 4th is 81. So this is now the 5th root of 81 x to the 4th. So 3 to the 4th power and then x to the 4th power. So I just distributed that power across those. Right? And that would be your final answer because the only goal here is to rewrite these things in terms of roots. And you'll also need to go the other direction. Right? Well, oops. Wrong one. Let's try this again. That's what I wanted. There we go. Okay, so the other thing that you may be tasked with is to take something like this. Well, I don't know. Yeah, we'll do that. Um, what do I want? No, I don't want that 3. You sure take a long time making up your mind. Yeah. Okay. Let's just do this. Let's do x to the fourth, y to the third. We'll just look at that. Okay. So as a root, it looks like this. But if I'm going to rewrite it in terms of rational exponents, this ends up being, let's see, the index is 7. So I'm just going to write it this way first. X to the fourth, y to the third, raised to the 1/7. Right? So if you're just converting the root itself, it's a fraction with the numerator of 1. Once I'm here, again, I'm going to distribute this fraction across here. So 4 times 1/7 is 4/7, and 3 times 1/7 is 3/7. Right? So you should be able to go and do things like this as well. If I have something like, the eighth root of 2, you should be able to say, oh, that is 2 to the 1/8 power. Right? And so those are the things I want you to be able to do. I want you to be able to convert back and forth between roots and exponents. Um, uh, and simplify things a little bit, but mostly it's the conversion back and forth because we will be doing things with that this semester. So you do need to understand that. Now, just real quick, I just wanted to show you some of the things that do happen. I haven't put these in the homework, but these are uh, just ways that this idea gets used. Um, so first of all, if I have something, well, let's try this with, there we go, with the pen turned on. If I have something like this, if I have like the cube root of x times the square root of x, right? Under normal conditions, when the indices of the roots match each other, you can just multiply the radicands. It would just be x times x, you make an x squared. But these don't have the same index. So what you end up doing is this. This is x to the 1/3 times x to the 1/2. Now, I have like bases, and I'm multiplying them. So all that means is I need to add the exponents. Right? So that means that this is now x to the 1/3 plus 1/2. So I just need to do the 1/3 plus 1/2. Right? If I find a common denominator, this is 2/6 and this is 3/6. So this ends up being 5/6. So this is now x to the 5/6. Well, this can be rewritten as a root also. And so multiplying these two guys, if I come up here, I can say this is now the 6th root of x to the 5th. And so I've taken two roots and I've rewritten them as one root. And so that's one of the ways that this thing gets used, right? Because it is very useful to be able to combine things like this. There are many times in math when you have to multiply dissimilar roots. So that's one of the areas that this gets used. I just wanted to give you an example of that because we're not quite at the point where we will be using this just yet, but we do need to know it for later on this semester. All right, there we go. So, all right, so that concludes the our lesson on radicals, our review lesson. So until next time, keep your pencils and your wits sharp. That's a really cheesy line, Mr. Brian. Yeah, well, I like to keep cheesy lines around, just in case so.